Okay, good morning, Dave. This is Dave Hobro. Dave, how you doing?
Very well, thank you, John.
Excellent. Thanks for joining us this morning, Dave. So this is we're in week 4 now of the project, and the students are the kind of position they're at is that they've all chosen an article and they've stripped it down and they've kind of worked out what it does and sort of from a system point of view how it works. So I think the timing of your presentation couldn't be better. Really, it's an ideal time to understand a little bit about how we design things for repairability.
Right,
So
lovely. Well,
with
I
that,
hope that this is a timely presentation.
absolutely. I was also having a chat with the students as well about how you and I know each other and our sort of mutual interest in amateur radio and technical things like that. So although the students aren't here and we're recording it this morning, I think there's a good connection between what they're doing and our background. So over to you, Dave. Anyway.
Right, thank you, John, and welcome, students. Designing for repairability. Sadly, in the modern world, things are not made to be repaired. We're in a throwaway society, so to be able to repair things is a useful commodity. So what we're going to cover is some good design basics, some good designs and some illustrations of bad design, and manufacturing process and control, because you can design something to be as good a product as possible, but when it actually comes to the implementation in manufacturing, they can often let things down. We'll look at FMEA, which is failure mode evaluation and analysis, and the environmental issues. So starting off, my background, I spent 30 years with Carmichael's making fire engines, starting off as an apprentice and ending up as head electrician. I then left and started working for myself and ran a very successful electrical design business with a wide range of manufacturers, mainly vehicle, whether it's posh cars like Bentley or useful materials handling equipment like class telehandlers. And then as I was coming up to retiring, I started to volunteer at one of the local repair cafes. The repair cafe movement is growing. In Worcestershire, we've got at least 5 around the county, and they normally meet on a Saturday. So
Dave,
they should be.
Is the repair cafe something that the students could get involved in, do you think?
Yes, it is indeed, John. All you need is a little bit of mechanical knowledge, but quite often you'll learn quite a bit by just actually going up and watching what the repairers are doing.
That's a good point. That's exactly how I started. I'm also in the repair cafe, and the first time I went, which was only last year actually, I spent the first session just sort of sat by somebody and taking it all in and understanding what they were doing. So I found it was really kind of welcoming and non-threatening and non-pressure sort of situation. So yeah, if there's some if that's of interest, then look up the local repair cafe.
Oh yes, definitely. The attending a repair cafe, you'll see some of the good and the bad design points of design engineering, or lack of it, so to speak. So I normally help out at the Bewdley Repair Cafe, and this is a scene in the Bewdley Repair Cafe. As you can see, there's ladies with sewing machines, because believe it or not, a lot of people don't know how to repair garments or whatever. The gentleman in the brown coat, he's an electronics repair expert. And across the other side of the room, there are people who repair clocks, ornaments, things like that. And just out of screen to the left of that slide are the guys who sharpen the shears, scissors, drills, whatever needs sharpening. And as you can see, there's quite a list of things that get looked at. I think one of the strangest ones that I ever had to repair was somebody brought in a small concrete mixer, and it had been badly stored, and basically what had happened, the water had got into the back of the motor and the whole thing was seized up. But it wasn't a write-off, although it said B&Q on the label. It was actually made by a company called Benford in Coventry, so it would have been a standard item that B&Q had made with their label on it. So hopefully that was easy to get repaired. We don't just repair domestic appliances. Occasionally we get toys brought in, and here's two of the repairers looking at a Hornby 060 pannier tank, and I think the problem with that was the electrical pickup on the front wheels was not making contact all the time. And my best claim to fame with the Repair Cafe is I managed to fix Buzz Lightyear. Lady brought it in with her two children, and Buzz Lightyear wasn't doing anything. It had been simply made rather than crudely made. So once you unclip the battery pack off the back, there was two screws, and the front and back of Buzz Lightyear came apart. And once I'd got him apart, the problem was obvious, because the contacts had spread slightly. So it was just a case of pinch those up, screw Buzz back together, and he went to infinity and beyond.
Nice one.
So
nice one. I think just you say that you talk about that, Dave. I mean, it sounds as though that's just a problem with maybe batteries being taken out, the sort of repetitive nature maybe of it. But we were taking apart some laptops in the laboratory sessions last week. We got a bunch of, I think it was 10 laptops, and they were, every time we had a lab session, the course's laptops had been taken apart and put back together. And it really, at the end of the sessions, the laptops were really, we got screws in the wrong places. Some of the plastic stems had broken off, because clearly these things are not designed to be taken apart and put back together on a frequent basis. It's build it once in production, and then maybe it might be taken apart once in its lifetime and put back together, but that's it. Certainly when we were taking them apart 6 or 7 times during the week for lab sessions, they really started to fall apart by the end of that.
Yeah. I mean, Buzz was really well made for something simple, because all the problem really was the battery pack held 3 batteries, and there was 2 metal blades that pushed into a recess on the back part of Buzz's body, and the 2 metal grips had just spread slightly. So it was a case of squeeze them back up, and Buzz went to infinity and beyond.
Nice.
So there was a very happy couple of young children left the Repair Cafe with a fully functioning Buzz Lightyear. So it's nice to be able to fix some of them, but looking at some of the things that come in, they are made never to be repaired. One lady brought in a beautiful CD player, which had stopped working after about 12 months. And once we took the lid off, it was obvious what was the matter because part of the power supply, there was an integrated circuit, and there was a big hole in the top of the integrated circuit where it had exploded. And to make matters worse, they put grey paint over the top, so you couldn't read what the part number of the integrated circuit was. So that one, I'm afraid, was consigned to the waste. It couldn't really be recycled, and there couldn't really be any use for the bits. Quite often, you can strip things down to make other things from. What makes a good design? Probably the easiest thing to say is keep it simple. Here's a good example of a simple set of connections. The standard 1/4 inch blades. They've been around for years. They go via various names, Lucar, Faston, etc. It's a standard 1/4 inch blade, and they're all interchangeable. Their biggest use is probably in the motor vehicle market, where if you look under the bonnet of any vehicle manufactured probably before about 2000, there are loads of these push-on blades on the coil, temperature sensors, pressure sensors, all the way around the vehicle, and probably on the front and rear lights. So it's cheap, it's simple, it's reliable, and it doesn't take a great deal of tooling to keep them connected. Some of the connectors have a little lock to prevent them shaking off. All you need to do is just put a screwdriver under the end of the terminal and just gently prise it up, and the latch will just push back out of the way. The other place to keep it simple is the way you fix things together. There's 4 examples of good, simple fixings. Slots, cross points, or in the case of the one at the upper left-hand end, a cross between a slot and a socket. You don't need all that many tools to put together or to take apart anything that's been held with those sort of screws. And that's basically 10 screwdrivers, a selection of cross point and standard blades, which will cover most things that are held together. Some of them have long blades on because some manufacturers decide to put their screws down holes to keep them out of the way. That's perfectly fine. Most screwdrivers will get to screws down the bottom of the holes. A lot of manufacturers, for whatever reason, are going for security screws, Torx, etc. So if you start going to Torx, spline, whatever, that's just a selection of some of them. There's Tri-Wing, there's what they term snake eye, which is a fork with 2 pegs on it. So you're suddenly looking at least 90 bits to be able to dismantle anything. So if you're holding it together with screws, put some decent posi drive or plain ordinary slot screws or slot-headed screws in to repair it, or hold it together, I should say. Another point to good design is how easily you can repair it. And here's a domestic appliance that goes back probably to the 70s, 80s, the Swan electric kettle. No complicated switches, it's just basic basic, simple design. Stainless steel body. Screws that hold the handle on are either Phillips or slot head. So there's very, very little to go wrong other than the element. And to change the element, it's a simplicity in itself. There's actually no screws holding the element in. It's just that threaded black back collar screws over the end of the element, and there's a rubber washer either side of the kettle body to prevent it leaking. So simple design that will be easy to repair. But the thing is, when they made those things, although you could get the replacement elements, they tended to last quite a time. I've got one of these kettles down at my caravan. It's got a dent in the side, but it works perfectly well. So long may it continue. Another item of design, the clock on the cooker failed, and that meant that there was no way to set the timer up, so you could have the oven operating automatically off the timer. And delving into the details, a new cooker would have cost over £600, and there's basically a lot of bits of steel that would end up being scrapped. Okay.
There's an important point there, isn't there, Dave? Because it's with electric cookers like that, the timers will inhibit the operation of the cooker itself, won't they? So if the timer fails, you can't. It's not just the case that your timer's no longer working. It actually prohibits the use of the device, doesn't it?
Yes, unless you've got some cookers, gas or electric, have got an override so that you can operate the thing manually. But as I say, the new cooker was over £600, and the safety features on the new cooker were not as good as this one, because the top of the cooker is a hinged down cover over the burners, which are gas. Now, if you happen to have the burners on and you just close the top cover down, there's a mechanical linkage which turns all of the gas valves for the burners back to the off position, so that when you lift the lid up, all of the burners are turned off. Modern cookers, all that happens when you close the lid on the cooker, it shuts off the gas, so that next time you lift the lid up on the cooker, the gas starts coming through because it hasn't turned the valves off. I think that's a really bad design, but it satisfies the safety regulations. So instead of scrapping our cooker and having to buy a new one for £600, looking on the internet to the place where I normally look for my spare parts, a replacement clock was going to cost me £38 plus VAT. So that's a cheap repair option, and it saves a lot of environmental impact with having to scrap the old cooker. But the biggest problem I had was there was no obvious way in to get at the clock, because the knobs cover the holes in the front panel, and the black piece down the side here were pushed in, and there was no screws on the visible on the side. So once I pulled the knobs off and opened the front of the oven, there was two screws. The one obviously is just the buffer, the big one with the rubber surround, to prevent break in the door on the grill. But the other one, the smaller one, up to its upper right, is the one that held the side on. But knowing how these cookers would have been produced on a production line, they would have started from the bottom or the inside and worked upwards and outwards. There had to be a way of getting in. So once you took out that smaller screw in the upper right, it allowed the side of the cooker to be sprung open. So once the side of the cooker was sprung open, lo and behold, a couple of screws. And there was a couple the other side. So take those 4 screws out, and the whole of the front panel slides forward on its wires. So just be careful when you're taking the panel off that none of the connectors get pulled off. And there was the back of the timer. So making a note of the old connections and the new connections, because there was a difference between the two, but made sure that they went back on the right way around. It was a simple case of getting the clock out, and they'd done a really good job of securing the clock into the panel, because there was a small flange around the clock unit, or the timer unit, and all you had to do was either squeeze those up with a pair of pliers or put a screwdriver down and very gently twist to push that hook away from the flange. And case of pop out the clock, swap the unit over and put it back in. Now on the website, that clock is used by 3 different cooker manufacturers. So on the bottom face, there's actually 5 holes, but on our cooker, there's only 3 that are actually used. So it's just a case of put the pins back in for the buttons, push it back in, and reverse the design procedure, or the disassembly procedure. So fairly simple repair, and the cooker is back in action. A few examples of how not to do it. Quite often, the way manufacturers design things nowadays, it's a destruction job if you want to get into it. We had an Electrolux cleaner. It's made and sold under the brand name of Electrolux in the UK, AEG in Germany, and Vampire in Austria. It's exactly the same vacuum cleaner, but depending on the market, they've given it a different name. So the design was constant throughout the range, and although it was a lovely, sleek, smooth design, fairly modern, I've got no problem with that. The big problem is when you need to come and take it apart, because there's no obvious, visible way of getting into it. When you look closer, the method of getting into it was actually to try and lever things like the hinges at the front here, and these 2 pedal units. One's the on-off switch and the other is the cable retract. And then there's 2 clips at the back, and basically all they are is a peg that fits into a hole, which is fine, but the amount of pressure you have to put on the peg to push it back to get it away from the hole, so you can remove the cover, often results in the fact that you're going to snap the peg off. So you're getting to a stage where it's, the further you go into it, the more you're going to destroy it. So I persevered with it, And to release these two, you have to lever the flaps up, and in doing so, you snap off what it's connected to underneath. So basically, it was a one-off assembly job. When I finally did get in there was 4 screws, posi drive, that held the motor to the base plate. It would have been nice if they'd have put posi drive screws throughout the design. Okay, if they've got to sink them down in a hole so they're not immediately obvious, then that's good. But not a very, very good design. As I said, it was an example of a once and once only. It got replaced by a Henry, which in terms of repairability is the exact opposite. The whole thing is held together with cross-point screws. The switches and the warning lights are current assembly or current manufacturing products in the UK. And for good measure, there's a wiring diagram in the back of the manual, which is something you don't often see these days. So good old Henry will be repairable for a number of years. Now, here's another what I say a bad example. The bottom of the kettle is held on with tri-wing headed screws.
So they're a special fixing, aren't they, the tri-wing, is that right?
Yes, yes. They're...
Because they kind of look like posi drive, don't they, or a Phillips head, but they're not.
Yeah, they've just got three recesses in them. But this was a kettle that we had. Quite a reputable make of kettle, but it failed, and it was actually the base that failed, and we'll come on to that in a moment. But once you get the tri-wing screws out and take the bottom off, you wouldn't be able to replace the element because the element has been force fitted into the upper part of the body. So if the kettle element goes, it's a write-off, I'm afraid. We did have one where there was a weep round the level gauge, so the thing would start to leak all over the worktop, so it got replaced. The other problem with a lot of these kettles that drop onto a base is the centre contact, which is a rounded ended pin, and you haven't got much contact area on the end of a rounded pin. So when it fits into the base unit, and here's a drawing of how the two connectors go together. You've got the hemisphere or the rounded end on the bottom of the kettle, and that touches a matching rounded face in the base, and there's a spring connection here for the electrical connection. But as you can see, there's only a very, very small surface area between the two, and as most kettles are 2000 watts or 2 kilowatts, that is a lot of electrical energy to try and pass through a small contact area. The result is that the heat builds up in the base unit, travels along the phosphor bronze spring, and the phosphor bronze spring loses its tension. So you get a case where there's insufficient spring pressure, so it's keeping it's not making as good a contact, so there's more resistance. More resistance results in more heat, so it's a vicious circle.
What would be better from the point of view of the design then, Dave? What do you think the kettle manufacturer perhaps could have done to improve that?
Quite simply, instead of having two hemispheres touching, leave the hemisphere on the kettle connection because you need something to allow it to line up with the other half. And basically, in the base side, put something like a metal connection shaped a bit like an hourglass, springy, so that when you push it, drop the kettle in, it's actually pushing the center pin into a sleeve, which gives you, which depending on the way you make it, gives you a lot more surface area for your electrical connection. So basically, if you imagine holding your one hand out as if you were going to grab hold of something and then pushing your thumb in the top, there's a lot of surface contact area between your hand and your thumb. So it would be the same with the kettle.
Mm-hmm. Yeah, I see. Okay.
But some of the best kettles are the ones that have the 3-pin plug in the back of them, because there's a good electrical connection there, and the connection is normally straight onto the back of the element. So if the element fails, it's normally 2 or 3 screws, and you can replace the element.
Mm.
So we've seen the good and the average. So let's have a look at a couple of bad designs of and how not to do it. Most of the students will be familiar with these plug-in power supplies, called quite often a wall wart, because it does look like a wart sticking out of the wall. Their main problem is they're totally sealed. They work on the basis that if you put the thing together and it works, great. Ultrasonically weld it together and it should last for a long time. That's okay, but quite often in a cost reduction effort, they'll take a lot of the components out, some of which are suppression components, and without those suppression components, it can lead to failure of the main unit. So
what do you mean about suppression there then, Dave? What's that term mean?
Right. When they're plugged into the mains is alternating current, and it's going from a positive to negative peak 50 times a second. Right. Well, that gets fed into the power supply in the wall wart, and they normally use things like switch mode power supplies rather than what we term a linear power supply that's got a transformer and a regulator. The switch mode power supplies do it all in one box, but to achieve the efficiency, they have to put a oscillator in there to up the frequency, probably to about 10 or 20 kilohertz, which quite often in a quiet room, if you put your ear close to the wall wart, you can hear a whistle. So what you don't want is those high frequency whistles going back onto the mains. So they put suppression components in to filter out those frequencies from running back into the mains. Now, occasionally they will fail. Some will fail spectacularly and actually explode inside the case. I had it was a computer power supply, slightly bigger than a standard wall wart, but the compression, one of the suppression components had failed, and it exploded inside the case, and the thing stopped working. And when it exploded, it had actually damaged the tracks on the printed circuit board. So again, it was a write-off, and get a spare or at least a replacement power supply from the dealer, which is about £30 or £40 more expense and more items to go to landfill. So I wonder if the students are thinking, well, he's preaching on about good design and bad design. As John has said, we've met through amateur radio, and one of my interests in amateur radio is construction. And this is an item I made some time ago to take the low-level outputs from amateur radio transmitter and receiver and feed them into this box and generate a couple of extra amateur bands. All home built, including the case, but all of the components on there, all the parts, the orange relays at the back, the fans, are all standard products. The relays are available from all the mainstream component suppliers. The fans are actually a couple of computer replacement fans, and the units inside they are in standard cases, and they are either surface mount components or components that are actually mounted through holes in the circuit board. And that was a design of mine. It takes all of the signals from these units, brings them together, and switches them depending on what the incoming signals are from the radio. The front panel meters are standard items. LEDs, standard 5mm LEDs that are, pence for each one. And the other part of this circuit board is a temperature monitoring system. Behind each of these boxes is a temperature sensor which monitors the temperature of these two heat sinks. And if they get too hot in transmit, this little integrated circuit is looking at the incoming signals from the temperature sensor, and if it rises above a certain level, it switches these two fans on. If the temperature continues to rise above another preset value, these two transistors are turned on, and there's a fan in the back panel which will pressurize the unit or increase the airflow, because when it's finally finished, there is an aluminium top cover, and the airflow is down through these two fans, through the fins on the heatsink, and out through the side of the case. And if either of the temperature sensors fail, either they lose their supply, electrical supply, or the signal fails to come back to the board. The board is designed so that all three fans come on at full speed, just in case there's a problem with either the chip or the sensors. The fans come on full blast, and a warning LED comes up on the front panel.
That's interesting. So you've clearly designed it to. So you thought about how it could fail, and obviously when you're using it a lot and the amplifiers are working and the heat's building up, that you've not only have you designed it to be repairable, but you've also included into the design safety features to try and take the heat away, and ultimately to put a warning light on and cut it off. Then.
Yep.
Yep.
Okay. That's one of the. Well, that's the main feature of that little integrated circuit.
Okay. Is that a circuit that you've designed and built then, Dave, or is that an off-the-shelf circuit?
The integrated circuit is off the shelf, but the design is one I put together, and this is the second generation circuit board because it's a green one which I had made commercially. The original one I made at home, well, it's here, with photosensitive copper clad board, and then etched it and drilled it. But when I did the second version of the design, I took advantage of the fact that because there's 12 volts and 5 volts available on that board, 12 volts is on the bottom side of the board, and the top side of the board is 0 volts and 5 volts. So there's no chance of getting the two voltages interconnected by mistake.
Okay, that's interesting. Yeah, yep. So you've taken account of the fact that you might be in there repairing it, and you've tried to make it as excuse the phrase, but idiot proof. I guess.
Yes.
Yeah. Right.
Yes. And extending to that point, all of these white connectors, they are standard off-the-shelf components. These are made by Molex in China, but there's also a company called JST who makes exactly the same connector, so they're interchangeable. And all right, it adds a little bit of cost, but if you need to take a board out to do a check on it or a modification, you're not unsoldering 30 or 40 wires, which makes life a lot more complex. So that's actually the physical side of designing looked at. As well as designing the product, you might well have to design part of the process. And one of the things is to make sure it's done right. This is part of one of the crockery baskets in a dishwasher, which was ordinary steel, which they'd welded together and then plastic coated. But it failed within the first 18 months. No, the first 12 months of its life.
That's terrible, isn't it? Because you'd expect, I mean, if you're going to make and sell anything or buy anything, you'd expect let's assume you're going to use it for the purpose and the duty that it's been built for, but you'd expect it to last sort of 10, 15 years, wouldn't you?
Oh yeah, definitely. And the problem here and on the next slide is that when they welded it together, the welding process, whether it's flame, electric arc or resistance welding, will also change the state of the surface of the parent metal. And going back to my days of making fire engines, when we had anything welded, whether it was steel, aluminium or brass, you always made sure that you got rid of all of the changes in the surface in the area of where the welding was done. Because if you didn't, we used a paint process and the paint process wouldn't stick. And it's clear on this one and on this slide that all the points where the plastic coating has failed is where the parent metal was not cleaned off properly. So as well as making sure you've designed it with the right components and that they can be replaced, you may need to get involved with the process, making sure that everything has been cleaned off properly and is good to be surface finished. And just as a matter of interest, this LG dishwasher replaced a 35-year-old hot point. The only reason we got rid of the hot point was after 35 years, the counterbalance springs in the door had failed, and we couldn't get them. We couldn't get replacements, and I couldn't get it re-engineered because of the way it had been made. So the LG dishwasher replaced, as I said, a hot point that was over 30 years old, and the baskets were as good as the day we bought it.
That's incredible. So from a design point of view, let's say I was a design engineer then. I mean, I might think, well, you know, actually making it's nothing to do with me. That's going to be the team in production, or you know, and it could be a different manufacturing site, couldn't it? Really, I might feel I've got no sort of direct control on that, but maybe I could, you know, maybe. I mean, how would I go about from a design point of view? How would I go about sort of controlling that process then? Would I create a drawing and say, look, you know, this has to part of the process of manufacturing. It has to be make it to these tolerances, but also clean these areas after welding, or etch it, or acid bath dip it, or something before. What would you think?
Any of those, John.
Yeah.
It could be a particular drawing detailing the process, or it could be a situation where the designer and the process engineer get together to create a process document.
Right. Okay.
So that you know, the important details, and to a certain extent things that would need to be inspected in the process would be highlighted,
Okay.
and that's a particular case in point that the designer and the process engineer would get together and put together this document that says that all welding must have whatever process that they use, as you say, acid etch, even down to shot blasting.
Mm-hmm, mm-hmm. I remember working in the car industry. I was working at Land Rover, and when we had production issues, the first line of defence would always be that we'd issue some kind of instruction to the teams on the track, on the manufacturing process, the track, to say, it'd be like a care point, and we would say, you know, visually inspect this as it's coming down the production line, visually check this and reject something if it's not as it should be. But that's not addressing the root cause. You know, the point was always to go back to the design and update the drawing, maybe take it from an issue A to an issue B in terms of a production release, and you would add on that detail, wouldn't you, and address it at the root cause, because you don't really want to depend on, you know, the teams on production to sort of visually inspect something for you. You want to make sure that the parts coming to the production line are right in the first place, and then all we have to do is to put it together.
Yeah, very much so. I know that when I've been working at Bentley and Case New Holland, quite often you would have to, from our point in the design department, we would have to create a process control sheet, and list the main points and the actions to achieve those points. So it's not just designing it, it's making sure that the process doesn't add any steps into it that can cause problems later on in life. As I say, the plastic coating on here on the LG dishwasher failed within the first 12 months, and its predecessor was over 30 years old, and apart from the two counterbalance springs on the hinges, the only problem we had in its long life was a little bit of sludge in the base. Stopped the water levels rising in a basically it was two halves of a blow molded shape with floats and switches on, and the water couldn't get in to trip the switches at the appropriate time. That was literally a case of take the pipes off the bottom, rinse it through, and it carried on for many, many years after that. And the clips were actually spring clips, which all you needed to do was squeeze the ears together with a pair of pliers, and they would slide off the pipe. So again, all you needed was simple tools to do the replacement. Now, something the students might get involved with is FMEA. It stands for Failure, Mode, Evaluation and Analysis. And an excellent example is our cooker. And it wasn't apparent until we slid the cooker out to get the sides off what the problem was. The failure mode was thermal. Failure modes are often classified as thermal, electrical, mechanical. You can have other failure modes as well. And this is how we did FMEA when I was working in Basildon for Case New Holland. So yes, it was a failure. The mode was thermal. The evaluation then was, why did it fail? And it wasn't until we got the cooker out to get the sides off that it was apparent that on the back of the cooker is a fan which blows air over top of the grill, and it comes out here where this arrow is. And that arrow is pointing to a full cooker width cavity, which when the grill door is shut, allows the air to blow out into the room, creating a very, very small curtain to prevent the heat coming up to the knobs up here. And for some time, my wife had been saying that the knobs on the cooker are getting very, very hot, and to the point where she was having to use the oven gloves to turn the burners up and down. And it wasn't until we got the cooker out that there'd been a build-up of dust on the grill, the back, the fan grill, and the fan itself. So the fan wasn't turning the air as efficiently as it should have done. So a quick run over with the vacuum cleaner to get the dust off, and the fan now runs at its full speed, and the air curtain that comes out from underneath the control panel keeps the control knobs nice and cool.
Isn't that interesting? You know, I've never even thought of that, Dave. I must have looked at our cooker loads of times, you know, putting stuff in and out of the oven, and realised there's a gap there, but it's right in front of you. You never kind of think about it. Well, what? You never think, why is that gap there? But of course, it's there for a reason. Somebody's put it there, and in this particular case, and what you're saying is there's a really good safety reason why it's there, and it is to keep the knobs cool. Of course, it is. Yeah. Brilliant.
Yes, it blows the air through and prevents the knobs heating up.
Yeah.
So that was the evaluation was the knobs were getting hot, and the analysis was, yes, they're getting hot because they're not getting the airflow in the air curtain to protect them.
Yeah, I see.
So, you know, FMEA can quite often sound complicated and a bit scary, but quite often it boils down to some simple steps, as it did in this case. Repairability will also help the environment. I'm not a a tree hugger by any means, but the more we can repair and keep our appliances going, the less impact it will have on the environment. We've only got a certain amount of resources on this planet. Okay, yes, you can recycle steel and aluminium and things like that, but it still needs to be made in the first place. So we need to be mindful of what we're using. So if you can make something that can be easily repaired with cheap and simple components, that's good. That's good. And our carbon footprint. I often struggle to understand how you can make an electric kettle in China, ship it halfway around the world, and sell it for £20. The mathematics doesn't stack up. But obviously, the further you've got to transport something, the worse the carbon footprint will be. If you make it in this country, then you're going to have a necessarily smaller carbon footprint. And the other consideration is the financial impact. And using our cars as an example, you go out and buy a car costing £20,000. That's fine. After 2 years, the battery fails. So you've spent £20,000 on the car, and it's off the road because the battery's no good. So do you scrap the car and buy a new one? Or do you go to Halfords and buy a new battery for say £60 or £70? When your car manufacturer buys his batteries, I'm going now to the days when I was at Bentley. Bentley would produce 40 cars a day. Each car had 2 batteries, so that's 80 batteries per day that they would use. So if you go to go to a supplier and say, right, I'm going to be using 80 batteries a day, and my production life of this model is going to be, say, 5 years. Your manufacturer, your component supplier, is going to come back and say, right, instead of charging you £60 for your battery, we'll charge you £10 for your battery. So that when your customer needs a replacement battery, you sell him one of the batteries, which we supply to you for £10, you sell it to him for £60, and your spares and service and parts operation has made a £50 profit. So all you're scrapping is a battery. And in fact, car batteries these days, they're not scrapped. They actually go back, they're stripped down, and all the components are recycled. So that the plate material will go back to the metal manufacturers, will be cleaned, melted down, and put back into new batteries. So there's a big environmental plus there, that the more you can make repairable and recyclable, the less impact there is, both on the wallet and on the environment. So some of the photographs I've done, some were supplied by John Reimer from the Bewdley Repair Cafe, and there's an interesting website if the students want to look at plastics in design, and it's called MODIP, Museum of Design in Plastic, which is part of the Arts University at Bournemouth. And there's some very, very interesting photographs of designs that go back probably to the 1930s when plastic started to be used in items. So, thank you to everybody for listening. This talk is not the definitive resource for making things repairable. It's just a few pointers, like cost reduction, and that it is something that you will end up developing in time, and you'll actually learn by actually doing what is a good and a not so good design.
Yep, that's great.
So, thanks very much, everybody, and
thanks, Dave. Yep, it's been fantastic. Thank you very much indeed, and thanks for working with us with the difficulties with the technology this morning. Really appreciate that. With regard to questions, Dave, is it okay if the students have questions? We've got a couple of Teams groups that the students can ping questions into. Write the questions, submit them on the Teams group. I can then grab those questions, and is it okay with you if I sort of forward them on, and you can give us a considered response if there's anything that's cropping up?
Yeah, by all means, John. Send them. You can send them to me on email, and I can either do individual replies and send them back so you can forward them on, or just do a group answer to all the questions.
That's fine. I'll tell you what we'll do. We'll leave it in the hands of our capable students then, and they can decide. They can decide how they want to. What questions they want to ask, and let's see what comes in, and we'll just deal with it in the best way. But that's fantastic. Really appreciate the time, Dave, and thanks for sharing your experience and knowledge with us. It's very, very relevant with regard to the projects that the students are doing in reverse engineering, and I think it's given us some really good insights, particularly as to different ways of looking at things that perhaps would be taken for granted and perhaps otherwise wouldn't see and quite appreciate in the same way. So much appreciated, and I'll forward questions on.
Thanks very much, John.
Okay.
And glad to be of some help.
No problem. Thanks, Dave. All the best. Bye-bye.
Thanks. Bye.